Our next speaker will be Sam Spiro from UC San Diego. He's going to be talking about card guessing with partial feedback.
So everything I say here is going to be joint work with Percy Diaconis, Ron Graham, and Shayuki. So this talk is going to involve some card games, and my friend Grace has graciously agreed to play some of them with me today. So Grace, the way this game is going to work is the following. I have a shuffled deck of cards. I'm going to pick up the top card. I want you to guess what the card type is. So whether it's a 7, king, what do you think it is?
Let's go with 10.
All right, it was a 5. But so now what's going to happen is I'm going to discard this 5 and pick up the next card. And given that I just discarded a 5, what's the one card type you should not guess here?
I shouldn't guess 5.
Exactly, because there's 3 copies of 5 left in the deck and 4 copies of 10. So do you have a guess for this, Grace?
I'm going to go 10 again.
Good. I was hoping you would. You got it. So we're mathematicians here, so we can consider like a generalization of this situation. So we're going to consider a deck of size mn, where there are n card types, and each appearing with multiplicity m. So for example, a standard deck of playing cards has 13 card types, 4 suits, so n equals 13, m equals 4. And the way this game works is I'll shuffle the deck uniformly at random. Then the guesser, Grace, will try to guess what the card is each round. Then I'll reveal what the card is, discard it, and we'll just keep going this way. And the score at the end of the game is however many points, how many times Grace correctly gets the card correctly. And this is what's known as the complete feedback model, because I give her complete feedback about what the card is each round she gets. All right. And, we're mathematicians here, so we understand what's going on mathematically. So we'll let G denote some strategy for the guesser, and we'll define CMNG to be the expected number of points you get if you follow this strategy in this game. And I'm an extremal combinatorial, so I care about maxes and mins of functions. So we'll let C plus be the maximum number of points you can get under any strategy in this game, and C minus the minimum number of points. And Percy and Ron proved the first kind of result in this area 4 years ago, which says that kind of the obvious strategy is optimal. In other words, if we're playing this game and these cards have been discarded, you can compute the probability the next card is a 7 or an 8 or a 9, and you should just intuitively guess the most likely card. And this turns out to be correct, and it's not. Whereas more impressively, they proved what these maximum scores are. It's m plus or minus square root of m roughly when the number of card types n is. So okay, that's all solved. So now we need to move on to a different game. And Grace, since you did so well, we're going to try a slightly harder game. So once more, try and guess what card type this is.
Let's go with a 6.
Okay. Now, what do you think the next card is?
Oh. That's not helpful.
Yeah, no, it's not at all. So this is what's known as the no feedback model, where I tell Grace absolutely nothing about the card type that was revealed. So this is much harder for the guesser, but much easier as a mathematician to analyze, because no matter what strategy Grace looks up, she can't do anything clever. So she'll always get exactly m points correct in expectation. But that was a bit mean, so let's try one more time, Grace, and then be a little nicer with you. So what do you think this card type is?
Let's go with a queen.
All right, no. So it might sound like I'm being mean to Grace and just telling her that she's wrong, but actually I'm giving her a little bit of information. She knows this isn't a queen, and given this isn't a queen, what's the most likely card that this is?
A queen.
Exactly. You're wrong again, but that is the correct intuition, because there are, for a fact there are 4 queens, but anything else could only have 3. So this is the model I'm really interested in, is the partial feedback model. So each round I just tell the guesser whether they're correct or not what the true identity of the card. And this is much harder to analyze because we don't know what the optimal strategy is going to say. And it's worse. You can still consider the strategy of, guess a most likely card type each round. It's a much more complicated function to work out what the probabilities are, but you can in principle do it. But even if you did this is not an optimal strategy. There are weird situations where you don't want to guess the most likely card for strange reasons. But nevertheless, we can still try and analyze the behavior of this game. So we'll let PMNG be your score in the partial feedback model using some strategy, and P plus P minus the maximum score. So we can get some trivial bounds. So we can always consider the strategy of guess 7 every single round, and that'll give you m copies of 7 correctly, and that's a lower bound for the best you can do. And an upper bound is the maximum score you can get with complete feedback is at most the expected score you can get with partial feedback, because if I'm giving you more information, that can only help. And by Percy and Ron's result, this is basically m when n is fixed. So in some sense, we solved the problem. This value here is asymptotic to m, and so is the minimum value. But that's kind of boring. So we're going to try and ask a more interesting question, and that is what happens now when m is fixed, the multiplicity of the card types, but the number of card types now is tending towards infinity. And here, much different behavior happens. So for example, we return back to the complete feedback model, and here the maximum score ends up being the mth harmonic number times log n. Well, the minimum score in complete feedback is now n to the minus 1 over n. So for m fixed, so before, when n was fixed, we had m plus or minus square root of m. So, basically the same value, whether or not we're trying to minimize. But now in this reverse regime, we have, as n tends towards infinity, the maximum number of points we get is tending towards infinity, while the minimum score is tending towards 0. So very different kind of behaviors in this regime. And now we can return back to our trivial bounds. Now we're considering this regime with m fixed and n tending towards infinity. We again have the lower bound of m, again an upper bound of c plus, which now is like log n. So now these bounds are much, much less trivial. One is basically constant, one's tending towards infinity. And our main results give improvements to both of these kind of trivial bounds. So first, we improve this lower bound by a bit. We get an extra square root of m factor as an error term. But most impressively, we show that this lower bound is asymptotically kept. In other words, you can get at most m plus roughly m to the 3/4 points correct in expectation using partial feedback. And just to kind of ground this, intuitively what this is saying is that, so again, with no feedback, you can only get m points correct in expectation. And basically this upper bound is saying that you can't do really much better with partial feedback in this certain regime. So this partial feedback is really not that helpful compared to no feedback when you're in this regime. Any questions at this point? Yeah. Yeah, so let me talk about a few, that's like kind of our main theorem. Let me talk about a few open problems. So first of all, we have these rough bounds, and we conjecture that the lower bound is closer to the truth. But we do not have to prove that. Another thing you can look at is this minimum score. So again, P minus is the minimum expected points you can get if you're trying to use partial feedback. And again, we can get kind of the analogous lower bounds or trivial bounds of m and n to the minus 1 over m. So again, a constant and something tending towards 0. And we can prove that the constant regime is closer to the truth. We have a lower bound of basically a half here. But we conjecture that the real answer is basically asymptotic to m, just like in that's like if you're trying to maximize your score. So in other words, we prove that if you're trying to maximize your score, you can't really use partial feedback to get many points correct, extra points correct. So intuitively, you can't also use it to get much fewer points than with no feedback, but we don't know how to do it. Okay, so now, Grace, we'll move on to the final game. So again, it's going to be similar to 4. I want you to guess what this card is.
Let's go with 3 this time.
All right, it's an ace. All right, so once more, what do you think this card type is?
I'm going to go with 3 again.
All right, you were unlucky. It was the second ace.
Ooh.
But oh well. Now, what do you think this is?
You know what? I'm going to go with the pattern and guess ace this time.
Oh, you happen to be lucky. Very good. Now, do you have any guesses for this fourth card, Grace?
I'm really hoping it's an ace.
Oh, wow, you happen to be guessing correctly. Very, very good. Yeah, so as some of you might have worked out, the probability of a randomly shuffled deck containing 4 aces in a row at the top is very unlikely. Most of this quantity here. So one of two things must happen. Either Grace is very unlucky with how the deck was shuffled, or I guess something's lucky, given how she ended up guessing, or the deck was not shuffled uniformly at random, which is exactly what happened here. So this was what's known as an online card guessing game, because I got to, because I could only do this trick of putting 4 aces off the top of the deck off the screen because we were doing this online. All right, but now we're going to consider a 2-player game played by Shuffler and Guesser. You can also substitute this with Sam and Grace, which was partially why I chose Grace, a G starting name, to be my volunteer. So first, I do my thing, which is I'm going to shuffle the deck however I want, possibly uniform random, possibly in a more complicated way, using some strategy S. And then I'm going to hand my deck over to Grace, and she's going to play the complete feedback model however she pleases. And I'll note that mathematically, this is equivalent to me just going each round and picking from the deck however I want. I don't have to really shuffle the deck beforehand. And this is really why I call this online card guessing, but that's just aside. Okay, so we can again consider the expected score now, not only when Grace does her strategy, when also Sam does his strategy. And so, for example, if I choose to shuffle the deck uniformly at random, we know exactly the kind of balance that Grace has with her strategy G. We know between these two things, in particular, she can get at most the harmonic number times log n. But you might ask, can I shuffle the deck in a cleverer way so that I can bring this number down? And it turns out there is. So I can shuffle the deck in such a way that for m fixed and n tending towards infinity, the best the guesser can hope to do is log n, which is significantly smaller than the mth harmonic number times log n, especially when m is fairly large. And I'm going to sketch what that strategy is for you. And it's something I call the greedy strategy. So the way it works is if there are card types remaining in the deck, I'll choose a card from each of these types equally with probability 1/, regardless of how many copies are in the deck. So for example, if there's 100 ones in the deck and 1, 2, I'll pick a 1 or pick a 2 with equal probability. So this is much different than what would happen in the uniform case where I would almost surely pick one of the ones. And you can analyze this game, this strategy, using some variants of the coupon collector problem, and that ends up showing that you can only get log n point expectation against it. And moreover, I can prove that this greedy strategy is the unique optimal strategy for me if I want to minimize the number of points the guesser gets. And it's even stronger than this. If instead I'm trying to maximize the number of points that the guesser gets, the greedy strategy is also an optimal strategy. It's not unique because of stupid reasons, but it's basically no matter what kind of game you're playing, like the greedy strategy is the right thing. And with that, I will end the
talk. Great talk. Let's go ahead and thank our speaker. Does anyone have any questions?
I think this was mentioned, but I think I just missed it in the online shuffling. What kind of feedback do we have for that?
Complete feedback. Yeah.
Okay.
So yeah. So like what we were doing before, like I revealed the ace to Grace each round.
Okay. I'm curious if you have results for small m and n exactly that support some of these conjectures, or if it just gets totally combinatorial and infeasible to like compute them for low n.
Yeah, so let's see which of these conjectures. So I don't think I have much. So I think I don't really have much evidence for either of these two things. It's annoying to work out computationally what the optimal strategies are for partial feedback. So I have a little data, but really not much. Okay, that's a good question.
Yeah, I can only assume it has to be really annoying to actually compute, huh?
Yeah, no, there is an algorithm to like work out what the optimal strategy is. Like you can do it for very small m and n, but like not enough to get these kinds of like precise error bounds of like square root of m or gas and pi m or whatever.
I think you mentioned earlier that in the partial feedback that guessing the most, like working out the one with the most number of cards left is not always the optimal strategy. Do you have an easy example of when that's not a great strategy?
Yeah, I did have a standard example. I don't remember what that standard example is, unfortunately. So no, I do not have one offhand. If you want to contact me again after this, I can pull up an example for you.
Cool, thanks.
I'll do it offline.
Yeah. Can I ask what kind of lines do these proofs usually follow? Like what kind of techniques does it usually involve?
Yeah, so that's a good question. So it depends on what exactly you're doing. So for complete feedback model, it's very combinatorial and so for complete feedback, we know the optimal strategy. So we just have to like, it's just this weird random process where like you're following this specific strategy and the deck itself can confirm real. So it's just computing the expectation of some weird random variable. So the proofs there just use some like Chebyshev's inequality, like base result from probability theory, and like a lot of precise counting. The partial feedback is much more complicated because again, we don't know what the optimal strategy is. So again, this ends up using some like combinatorial ideas where we want to, for example, if I tell you like a bunch of things are not sevens, and I want to tell you the probability that something happens after, it's like you need to count the number of permutations where like a bunch of positions aren't 7. So it's these weird kind of restricted permutations that you have to end up counting. So that's like the combinatorial side. And then you also have to do a bunch of like careful probabilistic arguments and make sure it interacts well with like the game theory side. So it gets involved, but like I use a lot of like things from different kinds of fields.
Cool. Thanks.
I think Alexander Clifton has his hand raised.
Yeah, Sam, I think yesterday in the open problem session, you mentioned that like the increasing permutation problem was related to this. And I think that one bound looks like the same thing. What's the connection there?
Yes. So you're absolutely correct. So an observation you can make is that in this game, you can consider the following strategy. Guess 1 until you get 1 correct, guess 2 until you get 1 correct, guess 3, and so on and so forth. So if you shuffle your deck of cards randomly, you can view this as like a Stirling permutation. And the score you get from using this strategy I told you in the partial feedback model is exactly this L of pi parameter I defined yesterday. So the expected score you get, the expected value of L of pi is a lower bound for the best score you can get with partial feedback. And the best score you can get with partial feedback is at most roughly n. So that ends up being the connection. So apologies if someone was not there for the session, but that'll take me too much time to go into those details.
Any other questions?
So you improved the lower bound on the partial feedback game. Are you aware of any strategy that always does better than the like obvious lower strategy, or no?
Yeah. So what's the obvious lower strategy in your mind?
Or the one that gave us the lower bound of M? I'm not sure.
Oh yeah. So I mean, we do have a strategy that gives M plus square root of M. So there is a strategy. So the strategy is also very simple. It's guess ace the first half of the round, and then if there were very few aces, then just guess ace the rest of the round. So you'll get exactly M points. If there were many aces in this case, then there were probably fewer 2s. So just guess 2s the rest of the game. So that's the whole strategy, and that gives M plus square root of M, and that's the best we know how to do. And we think that's basically the best you can do.
Thank you.
Mm-hmm.
Just curious, if you change ace and 2 to like 3 different card types or something in each third of the round, does this attain the same asymptotic bound? Or
yeah,
does
so
it
you
strictly
may
worse?
be able to improve the constant. We didn't fight very hard for that, but it'll still use square root of M. This is kind of like this is like an anti-concentration result kind of for binomial random variable. Like you expect, if you take a random walk, you expect to be like about square root of N off, and that's basically where the square root of M is coming from.
Okay, and a constant improving at a rate that it wouldn't give you any like log M factor on top of this?
No, or at least the offhand, like back of the envelope compilations I did, like suggested you would not be able to. Actually, I can prove that if you only use constant many card types in your strategy, you can't do better than M plus square root of M, because I could just give you complete feedback and you still wouldn't be able to do better than M plus square root of M. Okay. The more precise answer to that.
Okay, great talk. Let's thank our speaker again.